Hello everyone, this is Federico de la Peña, your professor in Geology 149, Earthquake Engineering, and today we will be talking about liquefaction analysis. This is just part of what we call the assessment. Okay? When you're making an assessment, the endpoint is to give a recommendation. Okay, so you're gonna do some investigation, and then whatever your findings are, you'll get some numbers. Whatever your findings are, you have to compare it against a standard or a threshold, and then you evaluate if the numbers that you're getting, for example, settlement, liquefaction settlement, are actually acceptable. If it's not acceptable, you have to provide recommendations on how to fix that issue, fix that problem or issue. Okay, and this whole process, okay, starts with the analysis or the liquefaction triggering analysis. Okay. In here, you're basically calculating the factor safety of the soil against liquefaction. And before that, you also have to screen out all the soils that are actually potentially susceptible to liquefaction. For example, gravels and clays are generally not susceptible to liquefaction. Okay. And even before that, you also have to determine whether the project actually needs a liquefaction analysis. And that can usually be determined from the standard that you're using. In the Philippines, liquefaction analysis for building structures and bridges and dams, I believe, are required. Okay. All right. And this is just the general outline of the lecture for today. Okay. Going to be talking about the liquefaction screening process based on the DPWH Bridge Seismic Design Specifications 2013, as well as the triggering analysis, which is based on Yaud and Idris 2001, also known as the NCER 1998. And then for the next lecture, we'll be talking about the liquefaction settlement analysis, which is based on the Idris and Boulanger 2008. All right. Just a review. Remember that the effective stress of the soil, okay, this is an important parameter. It controls the shear strength of your soil. Okay. The more effective stress, the more effective normal stress you have, the stronger your soil is. Okay, or the stronger the ground the stronger is the ground. Okay. When you have zero effective stress, it means your soil is basically completely loose. Okay. It, it's basically fluid and it cannot support any more load. Okay. So this is important, right? Now, effective stress is a function of your total stress. Okay, and total stress is basically a function of how much overburden you have above your certain point or above your soil layer. And effective stress also factors in the pore water pressure. Okay? And pore water pressure is a factor of how high is the water table. And another factor is whether the subsurface is actually being confined. Okay? So the more confinement you have, the higher the pore pressure you get. Okay? Other factors such as undrained loading, or basically when you're imposing load rapidly such that the excess water cannot drain out, that also causes a rise in pore pressure. So more pore pressure, less effective stress. Once this effective stress hits almost zero or very low values, you get almost zero strength of your for your soil. And that's a bad news for all the buildings, bridges, or structures that are lying above your soil. They're gonna collapse. All right, so that's the importance of effective stress. Now let's talk about liquefaction. Basically, it's a loss of strength. Okay, basically loss of effective stress in your saturated sands or sandy or silty soils. Sorry for the typo. And this happens when the shear stresses are large enough to cause your soil to contract. Okay? Basically, when the earthquakes are big enough, okay, or long enough, happening long enough to actually cause your soil skeleton structure to basically just um, they just collapse, okay, and the or contract. Sorry, so they just move into their pore spaces, and when the shear stresses are applied fast enough or large enough, it's possible for the existing pore pressure to be not be able to escape. So they just build up. Okay. So when you have enough buildup of pore pressure, you can lose a lot of effective stress during an earthquake. And when you just lose a lot of effective stress, the soil just ceases to exist as a solid. It turns into a fluid or a liquid. Okay, it behaves basically like a liquid. And you can see here in this diagram, you have here a schematic of the soil skeleton or the soil structure. You have here a drawing of the subsurface and the building or the infrastructure overlying your soil. Also see here the groundwater level. Now, prior to an earthquake, you can see here the soil structure is more or less each soil grains are actually in contact with each other. Okay? They're basically supporting each other. So they have a structure. Now, once you have an earthquake, you have here your seismic load. Your soil can generally just be they are literally shaken up. Okay, so they are shaken up. The structure is disrupted. Okay, and of course, if the load is big enough, okay, and there's enough pore space for the soils to move around, they can basically just the soil grains can basically just move around such that there's no more grain to grain contact between your soil grains. Okay, they're technically just floating in the water. Okay, so the soil here is generally contracting, but there's not enough. But the water here is not really draining fast enough. Okay, so the pore pressure is just building up, and the pore pressure is high enough that it's causing the soil grains to just float around. Okay, and eventually the water will just try to exit. Okay, due to the high pore pressure, it's like a can of soda that you just opened. So you have a lot of pressure in your can of soda, and once it founds and when you open your can of soda, your soft drink, or it will just eventually make its way out. Okay, just here you have a sand boil forming. Basically, the pore water pressure is high enough that eventually the water will just escape into through the cracks in the ground and into the surface. Okay? And the end result here is that the soils actually end up being more dense after the liquefaction. Okay, and all the water will just rise above. Okay? And of course, during that phenomenon, your building, of course, temporarily experienced uh, being over a soil that has no strength. Okay, so the building can tilt. It can also go undergo settlement. Okay, okay. Now we have different types of liquefaction. First, we have is the flow, what we call the flow liquefaction. Basically, this one occurs in structures or ground that are sloping or are actually high, especially applicable for dams and embankments where you have great heights. You know, dams can easily reach 50, few hundred meters of height. And of course, you have a lot of existing static shear stresses due to the height and the slope of your ground or structure. And typically, these are typically metastable or pseudo-stable. They're actually close to failure, or their factor of safety against failure is actually near, almost approaching one. Okay, so just now when you have an earthquake, okay, just a few cycles of additional dynamic loading from an earthquake can cause liquefaction. And when you get liquefaction, since your structure is already near failure, or it has a relatively low factor of safety against instabilities, okay, you're just basically triggering the failure of the slope by causing liquefaction. Okay, so the liquefaction here is not the main culprit. It's just a straw that broke the camel's back. So it's basically just the catalyst for your failure. Okay, sorry for my poor handwriting. So it's your catalyst. And yeah, basically liquefied soils have really low strength, and that can contribute to the slope instability of your structure or your ground. And since these types of liquefaction involve great heights or great slopes, it often ends up in a failure that is actually catastrophic, meaning it undergoes rapid failure. Okay? And this is an example of a flow liquefaction in the San Fernando Dam in California. Okay, 6.6 magnitude earthquake. And this is your dam. This is basically your dam. This is your reservoir. And you can see here actually there's some cracks here. The failure actually moved towards this direction. Okay. And other type is your cyclic mobility. And this one is, again, this is more triggered by the cyclic loading in contrast with the flow liquefaction where the trigger is just a few cycles of seismic loading. In here, the ground actually experiences a lot of cycles of dynamic loading. And eventually, this leads to liquefaction. And since a liquefied soil has a very low stress, it has a very low strength, the soil can either settle vertically, okay, in the case of level ground liquefaction, or it can also spread laterally in the case of lateral spreading. Okay. Now, if you have structures, buildings, bridges, and other objects overlying your soil, of course, your soil is basically liquid. It cannot really hold up any structure, overlying structure, so the structure will just settle vertically, okay, and can probably sustain some damage during the process. Okay, so cyclic mobility is commonly occurs in areas or grounds with low heights or flat gradients. Okay, and you have your two types: your level ground liquefaction, which is your classic. This is your classic liquefaction that occurs in your buildings and residential houses, okay, in flat areas. And you also have your lateral spreading. Okay, this one occurs in areas near your river banks, okay, or near coastal areas. And this one is an example of a level ground liquefaction, okay, which is a type of cyclic mobility liquefaction. This is your 1964 Niigata, Japan earthquake with a magnitude of 7.5. Okay. And what happened here is you have your apartment building complexes and the soil underneath them liquefied. Some of them just settled vertically, while some of them actually sustained a bearing capacity failure. So you have your building, and then the soil just got too soft. Okay? And also you have to factor in that during the earthquake, the buildings are just swaying back and forth, and that probably just contributed to the momentum of the building to rotate. Okay, and probably led to your bearing capacity failure. All right, this is an illustration of lateral spreading. You can see here before the earthquake, basically you have your flat ground with a shallow water table. Another important stuff here is you just have your river in here. Okay, you have a free face. This is your free face where your ground can basically move into. Okay, so this is important for lateral spreading. There has to be an open face. Okay, where the ground can go into. Right, and basically you also have a dry sand and silt, and below that is your saturated soil, okay, lying below the water table. And during and after the earthquake, okay, basically the soil just liquefies, and of course the non-liquefiable soils still sustain will still sustain damage. Okay? Okay. They're basically just like rafts that are floating on a water. So during lateral spreading, of course, the ground will just spread into an open space. Okay, as you can see here. Okay, more examples of cyclic mobility. This one is supposedly an example of level ground liquefaction question mark in Negros 2012. I place a question mark here because I found this from a website. It was labeled liquefaction, but it's not really specified if it's a lateral spreading or level ground. But I noticed here that it seems that this area is actually sloping. Okay, so I'm quite hesitant to label this actually as a level ground liquefaction. Okay? This could be actually more of a lateral spreading, or it could also be a slope-induced uh, seismic earthquake-induced slope failure. Okay? So it's really hard to know without actually getting the subsurface data on this area. Okay, so I'm just putting a question mark here. Okay, a classic level ground liquefaction will have sand boils, and of course it should occur in a flat ground. Okay? And we have another example here, a lateral spreading in 2015 Bohol earthquake. Okay, so this came from the FIVOX website, and they explicitly labeled it as lateral spreading. So yeah, it looks like the area here is quite sloping, and probably there's a river somewhere, but it's not just shown in the photo. Now, settlement analysis. We'll probably discuss this later on. But for now, I'll just define them. Of course, you know that soils consolidate when you have a load imposed by buildings or other structures. And of course, it will depend on the amount of load that you have. If you have light buildings or your subsurface is actually competent material, you might not get a lot of consolidation settlement. Now, if your structure is relatively heavy or your underlying soil is clayey or saturated clay, which typically is more compressible, you may get more settlement, consolidation settlement to be specific. And of course, buildings by nature, they can call they can tolerate some amount of settlement. Okay, they can tolerate a certain amount of total or indifferential settlement, and there are existing standards and guidelines for determining critical settlement. Sorry for that. Okay, and so you basically have to compare. Okay, so you can calculate the total and differential settlement. Okay, and then you can compare it with your allowable limits. Okay, now if they're exceeding your allowable limits, you have to do some engineering intervention. We'll be discussing that later on. Now, let's just define some terms in settlement. We have here your consolidation settlement. Okay, this is just due to the compression of soils over time due to load. Okay, so if you have a building, okay, over time, this will, after construction and during construction, the soil will undergo compression and you will get some settlement due to that. You also have liquefaction settlement. Now, this is more of a rapid, okay, this is an abrupt phenomenon that is caused by earthquake. Okay, so you have a liquefaction during an earthquake, and of course, liquefaction, you're basically squeezing out your water from the subsurface, and as a result, the soil will just settle vertically. Okay, so these are two different animals. Okay, and they have to be calculated separately. Okay, now you also have your total settlement. Okay, and this is basically your largest calculated vertical settlement. So let's say, for example, you have a project area and you have different boreholes. Okay, so whatever what and from the boreholes you can have your geotechnical data, and from there you can calculate the potential settlement that you can get depending on the size of the building that you'll be constructing. And whatever amount of settlement that you get from these different boreholes, you just stick with the largest amount of settlement that you can calculate. Now, differential settlement is basically the largest difference of vertical settlements within a structure. So to better define that, for example, you have three boreholes on a site. Okay, so borehole one has a calculated 100 millimeter settlement. Borehole two has 10 millimeters, and borehole three has 20 millimeters of calculated settlement. So you can easily see here that the biggest difference in settlement is between borehole one and borehole two. They have a difference of 90 millimeters. Okay, and that would be your differential settlement. Now, the total settlement here is basically the largest one. So you have here borehole one, which has 100 millimeters. So your total settlement here is 100 millimeters. Okay. All right. Now let's just skip back again to screening. Okay. Okay, so I made these a skip in the topic here, but let's just go back to the screening. So we do screening before we do the analysis, and the purpose of screening is to basically identify the soils that can potentially liquefy. If they can potentially liquefy, then we calculate their factor of safety against liquefaction. So this is just the step, like the step one before we do the actual analysis. All right, so you have different criteria here. You have you have your grain size. Generally, gravels are too rigid to liquefy. Okay, you can revisit your favorite soil mechanics textbook on why. Clays are too cohesive to liquefy. Basically, clays are they have a special interparticle attraction. Okay, they have a cohesion, and at certain times, this is enough to resist liquefaction. You also have your relative density or your stiffness. Okay. Relative density is applied for your granular soils, while stiffness is applied for your fine soils like clays and silts. Okay, so if the soil is relatively dense or relatively stiff enough, it can actually be enough to prevent liquefaction as determined from SPT and values of VS30. Where VS30 is your seismic shear wave velocity for the upper 30 meters. Okay. The higher the VS30, the more stiff your soils are, or in the more shear resistance the soils have. Saturation, basically all the soils that are above the groundwater table cannot liquefy. So basically, if the soil is above the water table, then the soil is probably dry, so it cannot liquefy. Now, what if the soil is actually frequently flooded? Okay? I mean, let's say you did drilling during a dry season, and this is very common in geotechnical investigations. It's better to do drilling during a dry season where, of course, the weather is favorable. You spend less time worrying about the rain, worrying about the safety of your personnel, and all that shit. Sorry. So yeah, it's possible that you did your drilling during a dry season and you found out that the water table is lower, is generally low, but you know for a fact that the soil is actually flooded or generally has a higher water table during the wet season. So of course you can just adjust the elevation of the water table. You can probably do some observations during the rainy season or just adjust the groundwater table to whatever you think is reasonable as long as you have a basis. Okay. Gradation, this is basically the sizes of your soil grains. Well graded, this means that so well graded in engineering convention means you have a good representation of all the grain sizes from small, medium to large, and they are continuous in distribution. In theory, this means that your soil has smaller spaces. So basically, if you have big grains, whatever space in between them, this can be easily filled up by your medium or by your smaller sized grains. So we have fewer pore spaces. You have smaller pore spaces here, okay? And generally, your soil grains cannot really move around during an earthquake, so they're less susceptible to liquefaction. Sorry, liquefaction. Confining pressure. Generally, the more confining layers, the deeper your soil is, the more confining stress you have. So you can just imagine if your soil is just being held down by a big dead weight, okay, and it can't really move around during an earthquake, so you can't really get liquefaction, okay. So if you have a lot of confinement, the soil would be too dense or too stiff to actually rearrange its soil grains, okay, during an earthquake, and cannot really liquefy. Geologic history. This is quite contentious because this is mostly based on U.S. studies. Okay? And in the U.S., they have a lot of different types of soils. They have their paleosoils or buried soils. Some of them are soils buried under rock formations, and of course, they're already compacted, actually compacted enough that they cannot liquefy. But if you're in the Philippines or you're in an area with really active geomorphology, lots of rains, lot of the surface sediments are continuously being reworked, okay, due to active tectonism, lots of uplift, and lots of erosion. Most of the soils that you will encounter are actually unconsolidated deposits, which is very common in the Philippines. Okay? Paleosoils, buried soils are not really that common in the Philippines. All right, screening criteria. There's a lot of screening criteria hanging around in the literature, but I'm just presenting you the one from the DPWH Bridge Seismic Design Specifications 2013. Okay, why? Because personally, we find this the least vague among the criteria. I mean, some criteria will just mention that the if the n value is more than 10, it's not liquefiable. But they don't really specify if the n value or the SPT n value should be corrected or not corrected. So at least for us, this criteria is the most most fleshed out. It's not really vague. I mean, everything is really completely defined. And this criteria is also very rigorous. Meaning it considers a lot of engineering soil properties. So let's go through this criteria one by one. Right, first question is whether the groundwater is deeper than 10 meters. Okay, if your groundwater elevation is like 11 meters below the ground, that is a no, and you don't really need to do liquefaction analysis. Now, if your groundwater, let's say, is 9 meters, then it's a yes. Then the next question is alluvial sand layer is within 20 meters below the ground. This is a bit of a misnomer because this is better spelled out as soil layer. I mean, alluvial sand layer. It's really it it just complicates the definitions here. Like how do you determine if the soil is alluvial sand? I mean, what is your specific criteria for saying the soil is alluvial sand? I mean, geologists argue over a lot over these definitions, and it's really just safer to consider all soils. Okay, so if the soil is within 20 meters below the ground, meaning the soil is not 20 is not deeper than 20 meters, okay? If it's yes, meaning the soil is shallower than 20 meters, you proceed with the next question. So you do some soil particle size analysis, okay? Next question is the D50. This is the D50. So D50, this is an engineering parameter. So imagine if you have a soil sample and you have a sieve, okay? If you if you pour your soil sample over the sieve and like 50% of the soil sample passes through that sieve, uh, whatever the size of that sieve is, that is your D50. So for example, if I have a sieve that has a size of 10 millimeters, so the holes in the sieve is 10 millimeters, and I drop a soil sample in the sieve, and 50% passes through that. That means the D50 of my soil is 10 millimeters. Okay. Now, if my sieve is like 2 millimeters in size, and 50% of of my soil sample passes through that, then that means my D50 is 2 millimeters. Okay. So if the D50 of your soil is like 10 millimeters or smaller, okay, okay, and then you should proceed to the next question. So what is the significance of this criteria? This criteria is trying to screen out the gravels. Okay. Basically, if your soil is containing a lot of particles bigger than 10 millimeters, probably it's a gravelly soil. So it's not liquefiable. Now, the next criteria is D10. Okay. Your D10 should be less than 1 millimeter. Okay. So, so again, D10, if I have a soil sample and I have a sieve that is sized, let's say, zero point 0.5 millimeters, zero point 0.5 millimeters sieve size, and I just pour the sample. Okay, if only 10% of the soil sample passes through that sieve, and then that means my D10 is zero point 0.5. Okay, so again, this is just part of the gravel criteria. I mean, if you have if the D10 of your soils is bigger than one millimeter, probably your soil contains too many coarse or gravelly sized particles, so they are not liquefiable. Okay, so but if your D10 is 1 millimeters or smaller than 1 millimeter, then you proceed to the next question. The next question is the fines content. Okay, so the fines content, this is the percentage of soil that passes a number 200 sieve. Okay, a number 200 sieve is a sieve that has a hole size that has a size of 0.075 millimeters. Okay, so 0.075 millimeters. Okay, if more than 30, so if you have a soil sample and more than 35% of the soil passes through that, so let's say 40% of your soil is passing number 200. So that means the fines content of your soil is 40%. Okay. Okay. So so if you have a lot of fines content, like more than 35%, you have to proceed to the next question. You have to check if the fines are actually plastic. Okay. So this next criteria, this plasticity limit test, is actually a representation of the cohesiveness of your soils. Okay? You will remember previously that I said that clay soils are generally not liquefiable due to their cohesion. And plasticity index is actually a good proxy test. Okay? Most cohesive soils have a large plasticity index. Okay? They're highly plastic. Okay, the cohesive soils. So if your plasticity index is greater than 15, okay, so the higher your plasticity index, the more plastic your soil is. So if your soil has a plasticity index that's greater than 15, like PI 16, that's a no, so your soil is non-liquefiable. If your PI is like 14, so that's less than 15, then it's a yes, and your soil will need a liquefaction assessment. So it's really a rigorous criteria. You have to check a lot of soil parameters. Okay, but generally you just have to remember that this criteria just wants to screen out the gravels. It also just wants to screen out the cohesive soils, and it also just wants to screen out the soils that are too dry to liquefy. Okay, so dryness of the soils, the gravels, and the cohesive soils, those are your main criteria in the screening criteria by the BSDS. Right, now let's discuss the liquefaction triggering analysis. And I'm specifying here the method of analysis using standard penetration test. Okay. I'm gonna discuss later why we are using this method, but for now, just follow this flowchart. We start with the data, with the SPT data, and then the groundwater table data, and then the grain size data, and the Atterberg's or the plasticity index data. Okay. From there, you can correct the SPT to what we call the N160, meaning the SPT should be corrected to 1 bar or one bar atmospheric pressure at 60% machine efficiency. And then the next step is to convert your N160 into a equivalent clean sand. So in here, we are removing the effects of fines content. Okay, so a clean sand is a soil that has no fines. It doesn't have silts. It doesn't have clays. Okay, so we call it a clean sand. And then from there, we calculate the cyclic resistance ratio, okay, based on the N160 CS. Basically, the ability of your soil to resist liquefaction. And then we scale or we correct again the CRR to the appropriate earthquake magnitude. Okay, because the default the default CRR is actually calibrated for earthquakes of magnitude 7.5. Okay. And then the next step is to obtain the peak ground acceleration. We discussed this before in the previous lectures using the Fukushima in Tanaka. And then just basically calculating all the possible earthquakes and looking for the biggest PGA. And then after that, we can convert the PGA into the cyclic resistance ratio. And finally, we just have to divide the resistance by the stress, and you will get a factor of safety against liquefaction. So if the factor of safety is less than 1 or equal to 1, then you get liquefaction. Okay. Right now, let's discuss SPT, or standard penetration test. So this is a on-site dynamic testing. Okay. And this is done by hammering a sharpened tube to the ground and then counting the number of blows needed to penetrate 300 millimeters of your soil. This is the most frequently used method because it's cheap and it's simple to operate. So you can see here the advantages and disadvantages. Right? So so advantage, it is simple. Disadvantage, you have energy efficiency problems, meaning it's actually quite hard to get consistent SPT readings. Okay? Um, Especially if you're doing the manual version of it, SPT. Okay? In the manual version, basically the hammer is being dropped by your operators. Okay? And depending, if the hammer is not being dropped vertically, this can cause some energy inefficiency problems, and you can get inaccurate readings. Advantage, it's suitable for many soil types, but again, this once you start encountering gravels, you can have a hard time getting samples, and you can also have a hard time getting reliable readings. Other problems with SPT is when you have like a soft soil, like a clay, but you have boulders or gravels embedded in the clay. This can fuck up your measurements. Okay? It can the gravels or boulders or cobbles. Uh, in geotechnical terms, they may not contribute to the strength of the soil, but once the SPT encounters that, you can get artificially inflated numbers. Okay? You can get artificially high SPT readings. Can perform in weak rocks? Yes, that's possible, but it's not really recommended. Available worldwide. Disadvantages, yeah, you can get this a disturbed sample. Basically, you're mushing up the soil, so its intact soil structure is not really preserved. Okay. You can also get unreliable readings in soft clays and silts. I'll discuss that later on. High variability, of course, due to the energy inefficiency problems. But if you're using a machine or an automatic SPT, this problem is mostly minimized. So this is your typical manually operated SPT. This is what we call the donut or the jar hammer SPT. This is your hammer, and you have a tube in here buried in the ground. And basically, you just have to drop the hammer, and you have here an anvil to receive this hammer. So this will be you'll be just repeatedly hammering this anvil to push this tube into the ground. Okay. And this is an actual SPT in operation. You can see here the jar hammer. You can see here the anvil. The tube is probably somewhere below the ground. Okay. All right. I talked about the energy inefficiency problems. You can see here the person is just basically holding the tube upright. Okay. So two things. No, this is a safety issue, and second, this also contributes to the energy inefficiency problem. Okay. Basically, the hands here are partly absorbing the energy transmitted by the jar hammer. Okay. So you're actually getting less energy delivered to your subsurface. And these are just example SPT photos indicating the number of blows taken to penetrate them. All right. You can see here in this photo, it looks like you have a poop here. But actually, if you'll notice, you have two photos here that have yellow-brown colored material. So these are actually your rock. I'd say a badly weathered rock. And in the other photos here, the dark colored material is your soil. So in here, this is actually the transition area where your soil is just starting to transition into your rock. And in here, you can see that you have actually a very high SPT blow count, 85. So technically, this is wrong. You're not supposed to reach an SPT greater than 50. Okay. And if you're gonna follow the ASTM guidelines, you're not supposed to have an SPT greater than 50. If you're Once you reach 50, you should stop doing the test and start uh, trying. You should try to core or remove any stuff that's actually blocking your SPT tube. So in here, they actually what happened here is they encountered a piece of rock. Okay, so they're in the soil, but they started encountering a piece of rock. But what they did is they just kept on hammering the soil. Okay, they should have actually stopped at SPT 50 and started doing the coring. Okay, so anyway, this is a good example. No, if once you start encountering particles of rock, you can get really high SPT blow counts. Okay. All right, let's talk about the SPT correction. To N160, so this is the SPT blow count normalized to an overburden pressure of approximately 100 kilopascals and the hammer energy ratio or efficiency of 60%. Okay. So I don't know why 60 is the standard, but this is just the existing practice. And the formula to get N160 is basically you multiply the N value by the correction for the effective overburden pressure as shown by this formula. So you need, so Cn is equal to 2.2 divided by the quantity of 1.2 plus the effective normal stress. Okay, so this is effective. Okay, acting on the soil layer divided by 100 kPa. Okay, so this is your Cn. Your Ce is your correction for the hammer energy ratio. So this will depend on the type of equipment that you're using. Borehole diameter, this will depend on the size of your borehole. Rod length, again depending on the depth of your drilling. CS is whether you're doing a sampling with or without the liners. Frankly speaking, I've yet to see an SPT being done here in the Philippines with a liner. Okay, so a sampling liner is basically a plastic liner that is used to improve the recovery of your samples. Anyway, these are the correction factors. So we have here for the energy ratio, the do not hammer is the manual method of dropping your hammer to advance your SPT sampler. Safety hammer, this basically you have a pulley. You basically have a pulley that assists in the dropping of your hammer. And then finally, you have your automatic donut type hammer. So basically, this is a machine operated hammer. And it has the highest efficiency. All right, so for the borehole diameters, you have these numbers depending on the size. You can either manually measure the size of the borehole, or you can just determine the size of your drilling equipment like NQ, PQ, HW, and from there you can determine the size of the borehole that is being made. Rod length, again, this will depend on the depth of your drilling. So you have to do this correction per soil layer. And then sampling method. Okay. So if you have again, as I've said before, most of the SPT methods I've seen in the Philippines don't really have any liners. Okay? People are too cheap for that. Now, correction of SPT into the equivalent clean sand value or the N160 CS. CS means clean sand. So why do we do this? So first, you have to remember that silts and clays, or what we call the fines, they have low permeability and they drain out water very slowly. Okay. Now we have what we call the concept of undrained strength, and this happens when the application of load is too fast. Okay. For example, in the SPT, when you're hammering the soil, you're actually applying the load here very fast. And if your soils are actually fines or silts and clays, there's a tendency for the soil to actually to have pore pressure build up. Okay? And when you have a buildup of pore pressure, remember the effective stress equation. The more pore pressure you have, the lower the effective stress and the lower the shear strength. Okay? Now, the problem here is that SPT is actually intended or made to measure drained strength, not undrained strength. Okay? And generally, drained strength is generally bigger than undrained strength. Okay. So yeah, the problem is when you're doing SPT on a soil that contains fines, the hammering action is too rapid and causes the fines to exhibit undrained strength. And as a result, the drained strength is actually measured instead of your drained strength. Now, the workaround here is to convert your SPT measurements into what we call the equivalent clean sand correction. So this is also called the fines correction. So we need this because the fines actually cause underestimation of the drained strengths of your soil. So it means if you have fines, the tendency is that your SPT values might be lower than what they should be. Okay. Right. Let's continue. Uh, Calculating the equivalent clean sand value or the N160S as per the Idris and Seed 1981 equation is as follows. So basically, you have to add the quantity of your alpha coefficient with the quantity of your beta multiplied by your N160. And you can see here the values of alpha, okay, and beta are or will depend on the amount of fines that you have in the soil. Okay, and I'm not gonna gloss over the details of this equation, but basically you just need to know the fines content in terms of percentage. Okay, to know the to know the alpha and beta values. Okay. Now, once you've done your clean sand equivalent clean sand correction for your soil, you can now calculate the CRR, or the cyclic resistance ratio. And this is basically the capacity of your soil to resist liquefaction. And here's the formula: CRR 7.5. And you can see here a rather complicated equation. I'm not going to discuss the detail of that, but basically you just need to know the N160 N160 CS. Okay, and note that you have a 7.5 subscript in the CRR, and that simply means that the CRR value is calibrated for a magnitude 7.5 earthquake. And again, there will be another correction for that, which I will be discussing later on. Yeah, other disclaimers: this equation is only valid for N160 CS that's less than 30. If your N160 CS is greater than 30, it simply means that your soils are too dense to liquefy and are classified as non-liquefiable. So we can see here, there is a really clear clause here that if you're gonna use the SPT data as a criteria for liquefaction, you have to do your corrections first. Okay? You can't just use a raw SPT data and call it a day and say that it is not liquefiable. That's wrong. Okay? You will see later in the examples that SPT N values can change a lot once you start applying the corrections. Okay? And corrections are very important because that's the real number corrections give you the real numbers. Okay? All right, CRRM, again, this is the correction for the cyclic shear resistance. Okay. If your earthquake source is not 7.5 in magnitude, you have to apply the magnitude scaling factor. So CRRM is the cyclic resistance ratio for your earthquake. Okay, for the magnitude of your earthquake in question. So if your earthquake is actually magnitude 8, sorry for my poor handwriting, okay, you have to multiply the CRR 7.5 by the magnitude scaling factor for this earthquake. Okay, so you have to multiply it by 0.840. Now for peak ground acceleration, again, we've discussed this previously. Basically, you can use the Fukushima and Tanaka equation and then look for all the potential earthquake sources within 300 kilometers. If you want to be safe, you can use 300 but most of the time 150 kilometers search radius should be enough. So you will check all the historical earthquakes. You can look at the USGS and FIVOX databases. You should also consider the potential earthquakes determined from geological studies. So basically, the FIVOX active faults and trenches map is a good source to see all the active faults. And then from there, you can just apply the Coppersmith equation to determine the magnitude of the earthquakes that can be produced by those fault sources. So once you've done that, you can just look for the biggest PGA that can be produced and whatever earthquake, and just look for the earthquake that produces that PGA, and that earthquake will be designated as your controlling earthquake. Okay? Or the basically controlling meaning the most important earthquake that you should be considering. Cyclic stress ratio, this is basically the load that is being imposed on your soil layer during the earthquake. And the equation is based on Seed and Idris, 1971. CSR is equal to your TAV. What's this? Sorry. All right, sorry. CSR is equal to your shear stress average divided by your effective vertical stress. But this can be also calculated by this equation term. So basically 0.65 multiplied by the quantity of your PGA, which is divided by the G, and then multiplied by your total stress in kPa, which is also divided by the effective stress in kPa, and then multiplied by a stress reduction coefficient. And you have a formula here for your stress reduction coefficient. Basically, you just have to know the depth of your soil layer, okay, and then use this equation, okay. And then next step is the calculation of your factor of safety. Basically, you'll be just dividing the CRR by the CSR, and if the ratio is less than or equal to 1, then the soil layer is liquefiable. If the ratio is bigger than 1, then the soil layer is not liquefiable. So note that some standards actually use 1.5 as the dividing line between the liquefiable and not liquefiable, but as a default we use 1. Okay, so just consult the standard that you're using. Okay, so yeah, just basically a liquefaction analysis. All these steps that we discussed before, you have to do that for every soil layer that you have. Okay, so normally liquefaction analysis is done using software or spreadsheets. Okay, as we will do in the next activities. And basically, to be able to do liquefaction analysis, just read these two references and you will understand the whole process and theory behind them. Okay, so you have here your Yaud and Idris 2001. This has a good discussion on how to do a soil liquefaction analysis, and this is the whole basis of my lecture. You also have your Idris and Boulanger 2008. They also have a good example on how to do analysis and also how to do a settlement analysis, which will be discussed in the next lecture. All right, thanks for listening.